this lecture, we are going to introduce an application of ideal gas law. Specifically, we're going to be looking at how we can calculate the density of an ideal gas. So to do that, we're first going to introduce the concept of molar volume. So the molar volume is defined as the volume occupied by 1 mole of a substance. Okay, so you have 1 mole of a substance. What volume does it occupy? Okay, and so when we're talking about molar volume and when we're talking about various applications of ideal gases and comparing, different results, what we find it useful to do is to agree upon a standard temperature and pressure so that we can do apples to apples comparisons quickly and efficiently. Okay, so STP is an agreed upon standard that sets the temperature at 273 Kelvin and the pressure at 1 atmosphere. Okay, so if we're at STP, then that means we're at this 273 Kelvin and 1 atmosphere. Then we can determine the molar volume of an ideal gas using our ideal gas law. So specifically, what we're going to take, we're trying to find the volume, we're going to take exactly 1 mole of substance, right? Because again, we're looking at that molar volume, right? We are going to plug in standard temperature, 273 Kelvin, and standard pressure, 1 atmosphere. Plug it all into our ideal gas equation, and we will come up with a value of 22.4 liters, right? In other words, the molar volume of an ideal gas at standard temperature and pressure is 22.4 liters, okay? So it doesn't matter what kind of gas you have. You can have helium, xenon, or methane gas, does not matter. If you've got 1 mole of a substance and you're at STP, then that gas will occupy 22.4 liters. Okay, so now let's, before moving on to density, let's do a quick little problem here. And this is a problem that oftentimes throws students for a loop. Okay, so be careful here. I want you to take a moment and I want you to consider the following question. If we're going to assume ideal gas behavior, I want you to look at each of these gases below and tell me which one has the greatest volume at STP. Okay, so you've got helium, 1 gram of helium, 1 gram of oxygen, 1 gram of argon, or they will all have the same volume. Go ahead and pause the video for a second and come up with an answer. Okay, so a very common mistake that I'll see students make is they will select D, right? So D is incorrect, and let's take a closer look as to why. Remember, on the previous slide, we said all gases at standard temperature and pressure or at some given temperature and pressure are all going to occupy the same volume, because again, ideal gas law does not depend or care about the identity of the gases under investigation. However, we are not given 1 mole of each one of these gases. We are given 1 gram. As a result, right, H2 is going to be our winner, because if we have 1 gram of H2, it has the smallest molar mass and it will therefore have the largest number of moles. So this choice A gives us the largest number of moles and hence the greatest volume. Okay, so be careful with those. Be careful to really read closely what the question's asking and what the answers are presenting. Okay, now we're ready to go ahead and introduce the concept of density. So remember, density, mass of substance per unit volume. Okay, so what we're going to do here is use this concept of molar volume that we just introduced and the concept of molar mass that we've used extensively throughout the course and set up a ratio of molar mass over molar volume to define the density. So notice that because both of these quantities are in units of moles, if we say look at nitrogen for the sake of illustration here, N2 gas, we can plug in that molar mass, plug in that molar volume, and if we're at STP, we don't even need to do any calculations there. We can use the fact that it's 22.4 liters. Moles are going to cancel out, and we will be left with a density unit. Mass over volume, grams over liters in this case. Okay, now of course we want to be able to extend this, and we want to be able to carry out density calculations under any conditions, not just STP, right? So what we want to do here is derive an equation for the density, right, that is, again, relies on this molar mass over molar volume ratio, but we're going to plug in the actual units and use the ideal gas law. So let's follow through step by step. Remember, molar volume, right, is right here defined as the liters per mole of substance. So if we're dividing by the molar volume, we're going to have moles up top and we're going to have liters on bottom. Right? Molar mass is of course grams per mole. So if we carry out this little unit cancellation here, we again arrive at a grams over liters. Okay, now what we want to do here, however, is introduce the thermodynamic variables that represent moles and liters. Specifically, we're going to use N, amount, over volume. We'll use a script capital M to denote that molar mass, as is customary. And then we're going to use the ideal gas law. Remember, PV equals nRT. We want to get N over V. So I'm going to move V down to this side. I'm going to move my RT down to the left-hand side. And we will arrive at the following relationship right here. P over RT times that molar mass. Okay, and so it's this relationship here for the density that's going to allow us to solve these density problems at arbitrary temperatures and pressures. So for example, let's calculate the density of nitrogen gas, now no longer at STP, but at 125 degrees Celsius and at a pressure of 755 millimeters mercury. Okay, so we are given temperature, we're given pressure, we need to find D. So what we're going to do first is, of course, map out what it is our objective is. Of course, we want to find density. In order to find density, given the molar mass, temperature, and pressure from the problem, we're going to use our relationship from the previous slide. Density is going to be pressure times molar mass over RT. Okay? Molar mass of N2, we're going to, of course, get that from the periodic table. Okay, once we have that molar mass, we can then start. We got to be careful. We can't just start plugging in directly. We have to carry out conversions to make sure that we're in consistent units. First off, we're going to be using ideal gas law or something derived from the ideal gas law. So we need to make sure that our temperature is in Kelvin units. When we're plugging into this expression involving the ideal gas constant, then we need to make sure that we're in consistent units. So we're going to use a gas constant in liters, atmosphere, mole, Kelvin. So we need to convert our pressure into atmospheres. Again, keeping track of those significant figures with underlines. And then once we've carried out the proper conversions, now we can directly plug into our density expression. And keeping all of our units around, we're going to see that our atmospheres are going to cancel out. Right? Whoops. Atmospheres are going to cancel out with the atmospheres in the gas constant here. Right? Moles are going to cancel out with the moles in the gas constant here. Similarly with temperature, and we will be left with units of grams per liter. Okay, so we'll do one final example here just to make sure that we're on the same page with how to carry out these density calculations. But this one, I want to look at it from a slightly different angle. Right, in this example, let's suppose that we have a gas and we know the mass of this gas. Right? We know the volume of this gas at 55 degrees Celsius and 886 millimeters mercury. And we want to use that information now to back out the molar mass. So this is actually a way that we could determine the molar mass of some unknown substance. Okay, so we're going to start off by writing everything we know. We know the mass, we know the volume, we know the pressure, and we know the temperature. Our goal here is to find that molar mass, or script M in the symbolism that we've been using previously. Okay, so what we're going to do first is use the ideal gas law in order to convert this pressure, volume, and temperature into number of moles. Then we are going to use the number of moles and the given quantity of mass in order to determine that molar mass. Okay, so we're going to need both the molar mass expression and our ideal gas law. Okay, so once we have those values in place, all that's left to do is make sure that all of our units are consistent. Right? Once again, we're using ideal gas law. We're going to use the gas law constant in units of liter atmosphere mole Kelvin. So we're going to convert atmospheres to pressure, or pressure to atmospheres, I should say, the temperature to Kelvin, and then we're going to plug directly into PV equals nRT. PV equals nRT, where we have solved for n, we will then end up with our number of moles of 9.7454 times 10 to the negative third moles. And then our molar mass will simply be the ratio of the mass divided by the number of moles. From the problem, we saw that there's 0.311 grams, right, in this sample. We now know how many moles are in this sample, and we can then identify the molar mass as 31.9 grams per mole. Okay, so that sums up our little application problem solving section where we can use the ideal gas law to discuss topics of density in the context of ideal gases.